All right, everybody. Today's lesson is on rational numbers. And I just want to start off by saying when we start talking about rational numbers here is we're really going to be doing the same things that we've been doing all year long, working with equations, solving equations, things like that. It's just now when we talk about rational numbers, there's going to be specific kinds of numbers that are also thrown into the mix. So rather than just working with whole numbers all the time, we're going to be working with some other numbers that we call rational numbers. And rational numbers are really numbers that we already know how to work with, such as fractions and decimals, whole numbers, and so on. It's just now by specifically learning this lesson, they're saying, okay, now let's solve equations with fractions. Let's solve equations with decimals and learn how to do some of those things. So let's start here with our first definition, which is definition of what a rational number is. Okay, and it says here a rational number is any number that can be written in fraction form. Okay, well, here's some numbers that we've already worked with. Okay, we've worked with negative numbers like -4, -3, -2, -1, 0, 1, 2, 3, ... They keep going, all right? These are all numbers that we worked with. These are called integers, okay, where we have positive whole numbers and we have negative whole numbers. Well, really, if you think about it, guys, any of these numbers, whether it's a whole number or an integer, we can take any of these and write it in fraction form, is what they're saying. So if I take the fraction, if I take -4, okay, I can make any of those numbers a fraction by writing it over 1. So all of these numbers are considered rational numbers. Let's do the whole number +3 here. Well, +3, again, you can always change any number into a fraction by writing it over 1. All right, what's new here today, guys, is they're saying not only are we still working with these same numbers, all of these negatives and positives are called rational numbers, but not only are those rational numbers, but if I throw in something here like, well, what's in between -2 and -3? How about something like -2.15? Okay, well, that's also called a rational number because I don't have to write it as -2.15. I could write that as -2 and 15 hundredths. So I'm able to write that as a fraction. So now we're going to have decimals in the mix too. Or things that are already fractions like between 1 and 2. What if I did 1.5? Okay, well, that's in fraction form, so that's considered rational numbers too. So rational numbers are positive whole numbers, negative whole numbers, when we throw in certain decimals into the mix, and any fraction are all considered rational numbers. We're just going to be using them all now in our lessons. So then the second definition is what an irrational number is. So if we know what rational numbers are, basically all the numbers that we've been working with already, what are irrational numbers? Well, the definition here says an irrational number is any number that as a decimal never repeats or never terminates. So what's an irrational number? If basically what that's saying is we kind of get what rational numbers are, but some examples of what might be irrational, because these sounds like really strange numbers. Well, irrational numbers are going to be numbers like pi. All right, numbers like pi, because we know pi is 3.1415926 ... Well, what happens with a number like pi is it never ever repeats. Like there's numbers that happen over and over again, but it's never a repeating pattern, and it's a number that never ever stops. So this is what we call an irrational numbers, numbers that never have a pattern, and therefore we're not able to write it in fraction form. Okay, even actually another example would be if you take the square root of any number that isn't a perfect square. So like something like the square root of 7 would be called irrational numbers. Okay. All right, so now what we're going to be doing in this lesson is kind of just practicing some of those things. If I have numbers, like example 1 here, am I able to take certain numbers and write it as a fraction? Because that's how you prove that something's a rational number. So example 1, show each number is rational by writing it as a quotient of 2 integers. As a quotient of 2 integers. Well, that's just a fraction. It's saying write it as a fraction. A quotient, well, a quotient is just the division of 2 numbers. How about this? If I change 7 to 7 over 1. Now it's a quotient because fraction bar means divide, and quotient is the answer to a division problem, and it's a quotient of 2 integers, okay, 7 and 1. So really all I'm doing is taking these numbers and changing them into fraction form. That's it. So part A, 7, I make it 7 over 1. I'm going to do part C for you here too. All right, taking 5 and 3/4. Well, this is in fraction form. The problem is that it has 3 numbers involved, 5, 3, and 4. And we don't want that. It says a quotient of two numbers. So what I basically need to do is change this to an improper fraction. If you guys remember how to do that, we're going to take the denominator of 4, we're going to multiply it by that whole number, which is 5. So 4 times 5 is 20. Then we add on that numerator 3, which gives us 23. Denominator stays the same, 23 over 4. Now it's a quotient of two integers, okay? Because the fraction bar means division, and there's an integer on top, integer on bottom. Okay, I'm going to let you guys do part B and part D. So go ahead and do both of those, and they'll be just like A and C, and then come back and check your answer. Okay, you're back. Part B, well, negative 10. I don't care that there's a negative on there or not. It makes no difference to me. I'm still just going to write it over 1 and make it negative 10 over 1. Okay. Negative 3.5. Again, the negative doesn't mean anything to me. I'm just going to bring the negative down to my answer. And then I do this, change it to an improper. 2 times 3 is 6, plus 1 is 7. Denominator stays the same. So I get a negative 7 over 2. And that's how you're doing on those types of questions. They're basically just saying, show us that it's rational. And they're asking you to do that by writing them as fractions, because our rule was rational numbers are any number that can be written in fraction form. So all of these numbers are rational. Okay, example 2. Write each decimal as a fraction. So now they're asking us to prove, prove that decimals can be rational as well. So again, the definition of a rational number is to make to change the number into a fraction form. So when I look at these two, I'll do part A, you can do part B, but part A is 0.85, and I'm going to say right now, I say that incorrectly all the time. 0.85, kind of like saying slang for the number, all right? It's not supposed to be called 0.85. What you really should be saying here is that the 8 is in the tenths place, okay, and that the 5 is in the hundredths place. Okay, if there was a third number there, it would be the thousandths place. And really, that's what I think you need to know is tenths, hundredths, and then a third decimal place would be thousandths. Okay, so in this case, tenths, hundredths, thousandths. Well, 0.85, and I'm going to go by that last number there, which is in the hundredth place. So instead of saying this as 0.85, I would read this as 85 hundredths. And then just think about that. If you're going to say that out loud, 85 hundredths, well, can I just write that as a fraction? 85 100ths. Isn't that just 85 over 100? Sure. And then, of course, even though the example doesn't say that we need to simplify, always, always, always simplify. We never, ever stop without simplifying. So I look at the 85 over 100. I know I can divide both of them by 5. So I'm going to start by doing that. 85 divided by 5 gives me 17. And 100 divided by 5 gives me 20. So my final answer, because we always want to simplify, no matter what, the question doesn't even have to tell you to, okay, is 17 over 25. Okay, you guys go ahead and start part B. And the one thing I'm going to point out to get you started, and then you guys can do it, this is a whole number, 4.125. Well, doesn't that mean when I do this, isn't that whole number just going to be the whole number on my fraction? If it's 4 and something, well, then my fraction is going to be 4 and something. So really all you guys need to do is change the 0.125 into the fraction. Okay, pause the video. Go ahead and do that. Okay, you're back. So I know this is 4.125. We already said that the whole number is a 4, so that's going to stay as a whole number 4. The 0.125, well, the last place here, this is our, so it's tenths, hundredths. This is going to be thousandths. I can barely fit it in there. Thousandths. So this is 125 thousandths. Okay? And then all we need to do here to finish off is just simplify this. Okay? Again, I know my whole number doesn't change. It's still going to be a 4. The 125 over 1,000 I'm going to divide. Well, I know 25 goes into both of them. All right? And when I do that, I end up getting 125 divided by 25 is 5. 1,000 divided by 25 gives me 40. Well, they still end in 5 or 0, so I can reduce again. Let's divide by 5, giving me 1/8. So the 0.125 became 1/8. The whole number was a 4. Final answer is 4 1/8. Okay, now let's go the other way. Write each fraction as a decimal. Okay, so now we're taking this fraction. Again, I know that the fraction bar means division. So what we're doing is just changing it back. Now, the first thing that we got to make sure we get right is which number goes inside. The first number always goes inside the box, no matter what. People mess that up all the time. They always think the bigger one goes inside. No, it's the first number, the numerator, always inside the box, which gives me the 8 on the outside. And 8 doesn't go into 3, so instead of a 3, I'm going to make this 3.0. Bring my decimal point up into the answer. And I go 8 can go into 30. It's going to go in there 3 times. That's 24. Subtract, I get 6 left over. I have to add a 0. Bring it down. 8 goes into 67 times. 7 times 8 is 56. I get 4 left over, and I have to keep adding zeros and bringing them down until I have no numbers left over and my remainder 0, which is what I'm going to get right here. 5 times 8 is 40. Finally, I get a remainder of 0. So 3/8 became 0.375. Okay? You guys go ahead and do part B on your own and let me know what you come up with. Okay, we're back. So what we should be doing is dividing here. Remember the first number, the 5, always goes inside the box, so the 11's on the outside. The 5, I'm going to make it become 5.0 and bring the decimal point up in my answer. 11 goes into 50 4 times. 4 times 11 is 44. So we get 6 left over. Add a 0. Bring it down. 11 goes into 65 times. 5 times 11 is 55. So I get 5 left over. Add a 0. Bring it down. 11 goes into 54 times. That's 44. 6 left over. Add a 0. Bring it down. 11 goes into 60. And you see what's happening here is we keep getting this repeating. The 0.45. 45 is going to keep going like that. As soon as you notice the repeat, you can go ahead and stop. Since the 4 and the 5 are both repeating, we put that repeating bar over both of them. That's what we call bar notation. Okay, now, when a decimal stops like this one in part A, 0.375, boom, it's done, it stops. This is what we call a terminating decimal. Terminating numbers, decimals, are numbers that just simply stop. They do not go on and on and on forever. Okay? Now, repeating numbers do go on and on and on forever, but it's a repeating number. Okay? Repeating. It's the same pattern over and over and over again. Both of these are rational numbers. A terminating decimal is a rational number because it's written as a fraction. And 0.45 repeating, well, that was 5/11ths to begin with, so that also is a rational number. Irrational numbers are numbers that do not ever terminate, and they don't ever have a repeating pattern. Okay, example 4. Order the numbers from least to greatest. Now, when we're ordering these things, the best way I can put it to you is we don't want to compare these things when they're all different. Okay, and the easiest way to be able to compare things is to make them all decimals. Okay, so if I were to go ahead and do that, all right, the negative 5/4 is negative 1.25. Okay, this one already is a decimal, negative 0.2. This one's a decimal, 4.31. Negative 3 is just like negative 3.0. It's the same thing. 5/2 is the same thing as 2.5, so that's 2.5. And negative 13/3, well, it's negative. I know 3 goes into 13 4 times, so that'd be negative 4 1/3. Then 1/3 is 0.3 repeating, so I get negative 4.3 repeating. So the best way, now I know we can do fractions and get common denominators and all that, but it's hard sometimes to come up with common denominators. So best way is just to change them all to decimals. And now let's compare. Okay, the ones I'm going to look at right here is the 4.31 and the 2.5. And the reason I'm going to say that I'm looking at those first is because those are our two positive numbers. So because we're ordering least to greatest, I know those are our two largest ones. Okay, I know that the 4.31 is bigger than 2.5, so I'm going to write this all the way over here as my largest number. The 2.5, now originally it was 5/2, and you always have to go back to the original form, 5/2. Okay, so I got the two biggest ones out of the way. Okay, I'm even going to go ahead and X those out now. Those are gone. Now I have to look at the other numbers. Okay, remember, as a negative number, really the larger the number means the smaller that it is. So when I look at this, this is a negative 1 point something, negative 0 point something, negative 3, negative 4.3. So the negative 4.3 is the furthest away from 0. That's the smallest. And that originally was negative 13 over 3. So that's now gone. Then I go to the negative 3, which was just a negative 3 to begin with. Okay, then I get to the negative 1.25, which was originally negative 5/4. And then finally that leaves me with only one, which is the negative 0.2. And there are all your numbers from least to greatest. But put them in decimal form first. All right, last problem. Write each repeating decimal as a fraction. Now there's a rule for why this works, but I'm going to save you the trouble and just say, you know what, just trust me on this. Here's the way you do it. When we're writing this as a fraction, okay, all we're going to do is take whatever number that is. So part A here is 93 repeating. Well, the 93 is going to go on top. Okay, but I know there are 2 decimal places here, and usually we think hundredths for that. But because it's repeating means it's not actually going to be a hundredths. Because there are 2 numbers that repeat here, it's actually going to be over 99. Okay, because there are 2 numbers that repeat, that's why there are 2 9s on bottom. Okay, now over here with part B, the negative 0.8 repeating is going to be a negative, first of all. And since it's the 8 that repeats, the 8 goes on top, but there's only one number listed there that's repeating, so it goes over 9. Okay, that one's done because it can't be simplified. I'm not done with part A though, because I can simplify that. I can divide both of those by 3. So always, always, always we want to simplify. 93 divided by 3 is 31. 99 divided by 3 is 33. So I get 31 over 33 there. You guys go ahead and try part C on your own. See what you come up with. Okay, should be back. So when we're doing this last one here then, all right, 0.125 repeating. Well, the 125 repeats, so that goes on top. Since there are 1, 2, 3 numbers that repeat, that means there are 1, 2, 3 numbers on bottom here. And then you got to try to reduce. And I'd say go through your divisibility rules and see if they work. In this case, you're going to see they don't work. That already is in simplest form. So we can just leave that one like that. And that's our lesson for today. We're done.